Calculus 2, we are going to explore exponential and logarithmic functions again for about 5 minutes and then move on. So what you hopefully know from your pre-calculus experience is that exponential function can be written in its general form as some constant b times a to x. And the most famous one would be e to the x. And the graphs look like this. This is for, oh, I forgot the k, that's why. K larger than 0, which is growth. And this is k less than 0, which is decay. And we know how to use this for a variety of applications, which is our next section, 6.9, with models, exponential models. So we're not going to do any of that stuff now. We also know that there is y equals b log a of x, which is the general function for logarithms, but then we can write as y equals ln x, which is the most used one because the base is e. Ln is just the lazy notation. Instead of spelling out log base e, every time, we just write ln x, and we all know it's log base e. The graphs for logs, well, we technically only consider one of them because, there we go, goes through 1, x, and y. We see there is the vertical asymptote at x equals 0. We see there is the x-intercept at x equals 1. We also see there are no y-intercepts because there's a vertical asymptote there, and so on. The major point is to understand that that the exponential function and logarithmic function are inverses of each other. Just going to check if the stream is going. Yes. So these two are inverses of each other. That means that if I say that f of x is equal to e to the x, then the inverse is ln x. And we know that for inverses, hopefully know, that if you compose function with the inverse, you will get x. If you compose inverse with a function, you will get x. That theorem was in your pre-calculus course. So that means that I take e to the x and I plug in ln x as the exponent, they cancel down to x. Or if I start with ln of e, we are still going to end up with x. So this is how both function compositions look like, whether you're composing inverse with the function or function with the inverse. So that's the preliminary. Oh no, one more. What was e? Does anyone remember the limit definition for e? Oh, you're going to need it in this class. N goes to infinity. Open parenthesis, 1. Exactly. Very good. So we're going to need this one actually for our course. So make sure you start that one. Compounding, yeah. So now, let's talk about today's lecture 6.8. We are going to reintroduce ln x now through the integral 1 to x of 1 over t dt. So that's the fun way to write ln x. That's the definition of the natural logarithm, actually. If you try to compute this, you know that integral of 1 over t is ln t, computed from 1 to x. So you go ln x minus ln 1, and ln 1 is 0. You see how easy that is to verify? Right? Do we all know that the integral of 1 over x is ln x? So integral of 1 over t is going to be ln t. So now that you have that, you plug in the upper limit, which is x, minus the lower limit, which is 1. ln of 1 is 0. We see that on the graph. ln of 1 is 0. So what we get is just ln x, which is exactly what the definition says. Now you can use this to prove all of those identities that you guys had for logs. Let's say ln xy is ln x plus ln y. ln x over y is ln x minus ln y. And ln x to the p is p ln x. So all these properties can be verified, can be proven using the definition above in the box. Now, as I said earlier, since this is not an honors section, you don't have to worry about that proof. But if you are interested in this proof, and you should be, it's in the textbook, or you can see me if you get confused, and then we can work on it during the office hours or something. Yes. With this one, right here. Yeah. So they give you a 2-page proof for these things. And the first example is just a basic U sub, where you get to use, first and only example is the U sub, where you get to use the ln as the answer. Now, guys, you are going to solve 5,000 of these integrals, which will have ln as the answer. So let's take a look at 2 of them. So the cheap one, what's the integral of let's say 3x divided by x squared plus 16 dx. So how would you do something like this? U sub. What's U? X squared plus 16. What's the U? There we go. You got your point. So now I'm going to kick 3 outside, and then I have to fix. I need a 2, so 2x and then over 2 outside. Because I need 2x dx. And I didn't have it, right? So I make it. 3/2 du over u. And guys, that's exactly like 1 over u times du, which is ln u. Plus c. And then we go with our favorite sentence. And the favorite sentence says what?
Actually, no.
All right, I'll see. Today is Wednesday all day, right? 3/2 ln x squared plus 16 plus c. Yeah, we're done. Yes.
How do you know when to use the absolute value?
Every time for this integral, right? Every time when you get the ln, you have to use the absolute because it's issue of the domain. Which here I can quickly explain that. So guys, what happened? I'm not sure. Everything is written down.
No, that's not what I meant. I meant
I integrated this. Integral of 1 over u is ln u. You're welcome. All right, so now, guys, why is it so that when you take the integral of 1 over x dx, you get ln absolute x plus c? So the first thing that I have to make sure you guys understand is that there is a function over here, call it f of x, and then there is another function over here called g of x. And what functions have are domain and a range, right? But domain is the one that we mainly care about because it's the set of all possible input values. So if you look, if you just had like this going into ln x without anything, think about it. On the left-hand side, you have a function like this whose domain is all real numbers except 0.0. And if you draw the graph for ln x, which looks like this, you still have no value at 0 because there is a vertical asymptote there, but you're also not allowed to plug in any negative numbers, right? So I hope you see a problem there. So this is over here, the domain is just x larger than 0. No equal sign. So x cannot be 0 to plug it in or anything negative. So looking at these two graphs now, you see that this domain is much bigger than that domain. So what do? We put the absolute value, so anytime you even put a negative number and so on. So what is this negative? So what does the absolute value do? If you plug in the absolute value, it's going to create one more branch right here, like that. It's still going to fail at 0, and it should, because the original function which you integrated contained the vertical asymptote at x equals 0. And now when you integrate it, the ln still has the vertical asymptote at the same point, it must, right? Which is x equals 0. But if you don't put the absolute values, you are not allowed to put in negative numbers. We agree on 0, but this one, you can put negative numbers. It's not going to be any issue. With ln, it is. So we add those absolute values there to make sure that we can plug in any number and solve. Make sense? So when do we use absolute value? Every time we do this integral. And you will be sick of this integral that has the ln substitution as soon as we jump into chapter 7. So within the first week. Awesome. The next part is the part on exponential functions. And the definition of number e couldn't be more weird, but it is what it is. It says ln e is equal to integral 1 over e of dt over t is equal to 1. Versus the other formula for e, which is the one that you should be remembering, the limit. It is. It's right there. Look. Yeah, I can zoom in. Yes. Yeah. Oh, just stretching? You stretch like this, man. I want to call on every time, man. All right. Just a whole bunch of equations and formulas which I want to list. This is the stuff that you know from Calc1. And if you didn't know this from Calc1, then you can send me your thank you cards in mail. So let's talk about integrals and derivatives with exponentials and logarithmic and be done with this. So where do we start? We start by first remembering that the derivative of e to the x is what? E to the x. It's itself. But then you say, didn't we talk about the chain rule, which means that I can actually have any function, not just function y equals x? That's live. And if we apply the chain rule, we have it this way. Are we all agreeing on this? Remembering it from Calc 1. Then we upgrade one more time because we realize that the base does not have to be e. It could be 2. It could be 7. It could be pi. So it doesn't have to be special number e. It could be any other number under the sun as the base, and then you have the function. So I hope, guys, you see that the last one on the bottom is the one that is the most general case of all of them. And that is equal to copy times the derivative times ln a, which is the base. Questions, concerns for the derivative of E? So just one example and then we're pushing forward. I would like you guys to tell me what is the derivative in respect to x of 2 to the power of x squared plus x minus 1. What is the derivative of this? Oh my God. Hey, that's it. Sorry. Don't have to distribute.
Oh, I thought it was, I thought you were recording and then using external. You have external.
It's Calc1, you better. We are reviewing Calc1 over here. Awesome. Now we're going to deal with the derivatives of ln's. So we have, again, the good old, what's the derivative of ln x? And you say? 1 over x. Awesome. And then you say, but wait. ln not of x, but of f of x. Any function. Well, you put the function as is, the argument of ln. Control C, Control V, right? And then the derivative on top. So you see the progression, starting from the basic case into replacing function x with general f of x. So that could be ln of sine x, and you should be getting cotangent as the answer, right? But wait, if you call now, right, you can get the most general case for free, which is log any base of f of x, which is get the function, get the derivative. So you see that it's progression from up there, and you just have ln a downstairs. And that is the most general case. Does this work? Well, the answer is obviously hell yes, because think about it. If a is e, then this becomes ln f of x, but then a is e, ln of e is 1, so this collapses into that. If f of x is x, and this is e, then f of x is x, derivative of x is 1, ln of e is 1, and you get the 1 over x. Right? So if you want to remember them all, that's the one you remember, and then these two will be consequence. Now we all know these two because ln is the most of the time there. But you are going to run into some of those log base 10, right, for waves and pH values in chemistry and so on. There are going to be a fair amount of these log base 10s floating around. Decibel levels, earthquakes, you know, they're out there. Ready for integration? Of course you're ready for integration. We're just reviewing, having fun. What is the integral of e to the x dx? Plus c. Okay. And that's it. Now, can I have the integral of e to the f of x? Yeah. Dx? Yeah, but only under condition that there is f prime in here. So that we can use u sub. Without that f prime, you can't integrate. And then if you are doing this with a base, any base, then it's still going to be a to x, but you're dividing by ln a plus c. So there they are. Box this. So what's the integral of ln x dx? What did you just say? The last thing you said.
I don't know.
Correct. Yep. We don't know what integral of ln x. We know that the integral of 1 over x is ln x. We know that. But we don't know what the integral of ln x is yet. We're going to do that in 7.2 after you're done with your exam. You choose to have one. So we'll deal with that later. Yeah, it's x ln x minus x plus c. But we'll get there. And we're done. That's 6.8. Just have a whole bunch of examples where we do use substitution. So enjoy the homework of doing a whole bunch of calculus 1 problems, which will practice your u sub. That's technically what the homework is. We just redefined in this and kind of systemized all of these derivatives and integrals for ln's and e's. So we're going to take a break. I will restart the stream. When we come back, 6.9 exponential models. We do the word problems finally.